Welcome to the Henry AI Labs walkthrough of Keras Code Examples. Keras has provided 56 code examples implementing popular ideas in deep learning. This ranges from the basics such as simple MNIST and IMDb text classification, all the way to cutting-edge research ideas such as knowledge distillation, supervised contrastive learning, and transformers. We'll also explore fun generative examples like variational autoencoders and CycleGAN. My contribution to these code examples is to explain every single line of code in each of them, walking through each of the individual Keras examples. I'm not the author of these code examples. Please consider starring the GitHub repositories to show support to the original authors. I'm really excited to present this code example implementing knowledge distillation in Keras. Knowledge distillation is the idea of having a teacher network label data for the learning of a student network. So instead of the student network fitting one hot encoded class label vectors, it's fitting this soft distribution that comes from the logits of the teacher network. And this has been really useful for model compression in papers like Distill BERT. The idea is you take a large high-capacity model like the BERT transformer neural network with 300 million parameters, and then you train it and you use it to label data for a lower capacity model, the Distill BERT model, to learn from those labels. And this results in transferring this knowledge that's learned from the higher capacity model into the lower capacity model, which is useful for reducing storage size, inference speed, and overall making this more accessible for people who are maybe using just a single GPU or just not the computing resources of what BERT is trained with, or say GPT-3, or most of these large language models are really, really massive models that require a lot of computational resources. Knowledge distillation has also been useful in just achieving state-of-the-art performance. In self-training with Noisy Student improves ImageNet classification, they actually scale this up, so the student network is actually a larger capacity model than the teacher network, and they iterate through rounds of this, and it achieves the state-of-the-art in ImageNet when the paper was released. Knowledge distillation has also played an important role in bringing the transformer neural network to computer vision. In data-efficient image transformers from Facebook AI Research, they use knowledge distillation to transfer the soft target distribution from the convolutional neural network into the transformer. So they have this teacher-student loop where the teacher is a convolutional neural network and then the student is the vision transformer, and this has resulted in state-of-the-art performance in adapting the vision transformer, or the transformer neural network, to image classification or say the object detection tasks that are frequently benchmarked with deep learning and computer vision. So this code example is going to show you how to implement knowledge distillation for yourself, one of the most exciting ideas in deep learning, and plenty of research opportunities to see what can be achieved with knowledge distillation. We begin with the standard imports: TensorFlow, Keras, Keras layers, and NumPy. So now we're going to be constructing a distiller class. As stated in this documentation describing the class, we're going to have a train step, test step, and compile, and we're going to have a teacher model that's already been trained, a student model to train, the loss function where we implement this custom loss, which has the difference between these two predictions with the student-teacher predictions and the student predictions. And then we're going to have the alpha factor to weight the loss, because in knowledge distillation, you don't only train on the teacher's labels. You're also going to train on the one hot encoded labels as well, and you're going to weight these two loss functions with alpha. So if you've never implemented a custom loss function or some kind of deep learning training framework where you have two loss functions, this is a great place to start, because we're going to be doing this implementation where we have loss equals self.alpha times this one loss plus 1 minus self.alpha times this other loss. So a lot of these papers, like just to take a random example, if you've read GameGAN, the way that they learn GameGAN and the way they put Pac-Man inside of a GAN, this research from NVIDIA, is they have several of these loss functions. And it's common in things like CycleGAN, the recent extensions to it, where you have these frameworks. There's many papers like this where they have multiple loss functions and they're weighted by these hyperparameters like alpha. So alpha would be an example of a hyperparameter of this knowledge distillation system. So we define our optimizer and then metrics to evaluate the performance. Our distiller class is going to inherit the properties of the keras.Model. So Keras has these built-in things. We've seen many examples in the Keras example playlist of overwriting Keras layers. In this case, we're overwriting the keras.Model itself, and we're returning a model. And this is useful because we're going to embed all of our training logic within this model, and it's a different way of structuring this kind of customized loss function and training curriculum that'll be more clear as we see the whole entire example. So in the initializer, we define our teacher, our student. The teacher is a pre-trained model, and the student we're going to be training from scratch with this new loss function. Then we pass in the compile argument. Compile is an argument with these keras.Model. You have things like model.compile, and then you pass in the optimizer, the metrics, and so on. So in this case, we're overwriting our compile function to have our optimizer, something like Atom, SGD, and so on. And we have our metrics, which is like things like categorical cross entropy or whatever we're going to be measuring performance with. Then we have our loss function, and then we have this customized distillation loss function that is the reason that we're doing all this. So we have the alpha, that's our hyperparameter, and temperature is another hyperparameter. What temperature does is it smoothens out the distribution that comes from the teacher. So the teacher might be really well trained, and it might put a massive density on one class and then no probability on the others, because it's been trained to do this with the one hot encoded class vectors. So it might say put 99% on cat if you're doing CFAR10, and then 0.0001% on the other class labels. But temperature is going to smoothen that out so we can get more of the prior knowledge about how much density the teacher model has put on each of these other classes. So now we're going to, we inherit the super.compile that as we're inheriting this keras.Model object in the argument to our distiller class, we pass in these optimizers, we pass in the metrics, and now we're adding our custom logic with the student loss function, distillation loss function, and then the alpha and temperature hyperparameters. So now we're overwriting the train step. So first we take in our data as we're train step. The argument is our data loader, whether it's the keras sequence object or if it's just fitting NumPy arrays or a tf.data object, whatever it is going to pass us a batch of data. So we're going to unpack the data into x and y variables. And we might use this, say we had a data loader like in contrastive learning that gives us x prime, all sorts of things that we can overwrite these custom training steps to unpack this data and then do customized things with it as we're implementing these research papers into this code that overwrites kind of the generic frameworks. So now we're going to do the forward pass of the teacher. So we have this pre-trained teacher network. This could be something like the keras.applications, ResNet, or any kind of pre-trained model. And we're going to get these inferences by doing self.teacher, and then we do the calling by just passing in the x's, that is this batch of data that we got from the data loader. And then we set training equals false because there's no gradients that are going to go back through this teacher network. It's only being used to label the data and then using these labels as targets for the actual training equals true shown here, of our student network. Now we're getting into the more interesting part where we're applying our training. So we start off with this loop of with tf.gradient tape as tape. This is one way of getting the gradients. You see how later on in the code we're going to do gradients equals tape.gradient. We can access the gradients in this tape variable. And this is one way of accessing the gradients, seeing them, and then having this way of apply the gradients to our trainable variables. This is just another way of overriding the gradients in the way that this works. You can maybe print out your gradients, log them to a file. You have more customizability with respect to whatever it is that you may be doing or whatever kind of thing that you're adapting this to. So we loop through this. First we do our forward pass with the students with the x's originally from the unpacking the data. Then we have the loss function. These are one hot encoded class label vectors, these y's. So we're going to first apply, say, sparse categorical cross entropy to these y's with our student predictions. And then we're also going to do the distillation loss with the teacher labels and the student labels. So the way that we're doing this is we're taking the raw logits. So what I learned yesterday is the student predictions, when you do this loss function, if you use sparse categorical cross entropy from logits equals true, it's going to apply the softmax. Softmax is this function where you do e to the activation divided by the sum of e to all the other activations as you're making predictions on each index in a class label vector. So what you're doing is you don't have to actually pass this final output through a softmax if you do sparse categorical cross entropy equals true. So that's just a little thing. I hope that didn't distract too much. What we're doing now is we apply the softmax to the teacher prediction, and then we're adding in our temperature parameter by doing this instead of, say, having the sparse categorical cross entropy from logits equals true between these two just raw predictions, because we want to add in our customized temperature. So hopefully now that I'm saying that, it's tying all this together. The reason that we're applying softmax here in the distillation loss is because we want to add in the influence of this hyperparameter self.temperature. And again, temperature and alpha are the two big hyperparameters that are controlling knowledge distillation. Alpha with respect to how much we're weighting each loss function, and then temperature with respect to how we're smoothing out the distribution from the teacher higher capacity, or in the case of self-training with noisy student, just any kind of teacher-student loop, and the way that we smoothen out the distribution so I can get more of the prior knowledge from the previously trained network. Now that we've defined these two loss functions, we tie them in together with our alpha hyperparameter. The alpha weights each of these losses, and then it's stored in this loss object. Then we define the trainable variables equals self.student.trainable variables. Our gradients is the tape.gradients, tape from with tf.gradient tape is tape.gradients, and then loss. And then with respect to these training variables, so we pass in this loss with our computational graph, and then we pass in the variables that we want to update with our backpropagation step. So now we're going to update the weights by calling apply gradients with the optimizer, say this is SGD or Atom or something like that, and then we're going to zip together the gradients and the trainable variables. So this is how you do this custom tf.gradient tape and apply these gradients in the training. And And you can maybe imagine weighting this, holding on to these gradients and applying it a second time. All sorts of creative decisions you can do with respect to trying to come up with research ideas for deep neural network training and the flexibility offered to you by tf.gradient tape and this kind of functionality. So then what we have is we have this metrics object as we're overwriting a keras.Models, and it returns this metrics thing. Say you're doing something like history equals model.fit, and then you want to index this history, and it has an updated dictionary of all these metrics. So all this is doing is it's just updating the state with the metrics. You pass in the Y labels of student predictions. Say this metric is probably something like accuracy. Accuracy is the most common thing to store in one of these metrics. So just updating the accuracy, and as you know how you do model.fit, and it's going to progressively tell you what's happening, it's going to be reporting the accuracy, and this is the code that you need to customly overwrite to see that, since we're overwriting this keras.Model object. So now we're looking at the test step. This is when you do something like model.evaluate and you pass in x test, y test. So all this is doing is you unpack the data, you run a forward pass on the student network, you do the student loss function. This is not the distillation loss function. This is something like sparse categorical cross entropy from logits. And then you update the metrics with the accuracy, comparing the y and the y prediction. And then you return the dictionary with the loss for reporting when you do something like model.evaluate. And you see that one line that's something like student loss or training accuracy, validation accuracy, something like that. So overriding this custom distiller class is really the meat of what we're going to be learning in this Keras example, but here's the rest of this that ties it together. So the next thing to do is to define the teacher network and the student network. These can arbitrarily be any kinds of neural networks. In this case, we have a higher capacity teacher with 256 and 512 that is the hidden dimension of the number of features in the convolutional network. And then we have 16 and 32 in the student. So this is an example of model compression. We're going to be compressing this teacher network into the student through the use of knowledge distillation and having this student network predict the outputs that come out of this dense layer pictured here, trying to match these two between the teacher and the student. That's kind of the idea of knowledge distillation. And then we have the student scratch equals keras.models.clone model student. This is where we're going to be cloning the model because later on we want to compare the accuracy when we do knowledge distillation compared to just training the student network from scratch. And here's a neat trick to do that. Another way to do it might be to save the weights and then load the weights from a checkpoint, but here's another way of doing it if you're curious. The next step in training any deep neural network is to define a data pipeline. In this case, we're using the MNIST dataset, and we load it easily by just using keras, the datasets.mnist.load data. We normalize the x's by dividing them by 255. This keeps them between the interval of 0 and 1, and then we reshape them to be compatible with the image organization. I think originally it's maybe 784 by 1 vectors or something like that. I'm not sure exactly why you have to reshape the MNIST data, but that's what this is doing, is reshaping the tensors of the original shape of the MNIST data that's built into Keras datasets. So the next step is to train the higher capacity teacher network. So we do this by first compiling the teacher model with the Atom optimizer. This is the thing that I was talking about earlier, this sparse categorical cross entropy from logits equals true. This means we don't have to put the softmax layer at the end of this. It's going to automatically apply it to this output of these dense 10 logits, and it's going to apply that and adapt it into sparse categorical cross entropy loss. And then we see how we pass in this custom metrics relevant to our discussion on overwriting the keras.model with our distiller. This is the output now that we've passed in this custom metric using not just accuracy, but sparse categorical accuracy by passing in this metric. So then we do teacher.fit and teacher.evaluate, and we step through the data. I think we run through it about 4 epochs, or we have 5 epochs, and we end up with this loss with about 98% accuracy. MNIST is pretty easy to model with these convolutional networks, and this is the evaluation of our x test, y test, where we get the raw loss and then we get the sparse categorical accuracy as the output from this test step. As we see when we overrid our distiller class, we have this test step as well. This is what you're doing with respect to model.evaluate, or as it's iteratively stepping through with a validation set in something like model.fit, where you also pass in validation data. So now that we've trained our teacher network, we have a pre-trained teacher network to pass in as an argument to our distiller keras.model. So we define the distiller with the student network that we defined previously with the 16 and 32 filters in the convolutional layers and our pre-trained teacher network. So now we compile it, passing in the Atom optimizer, sparse categorical cross entropy for the metrics on the labeled MNIST dataset with the 1 hot encoded labels for the handwritten digits of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then we have the distillation loss. So here's a really interesting thing. We're doing the KL divergence between the teacher's probability distribution of the logits and the student's probability distribution. So Kullback-Leibler divergence, shown on this Wikipedia page, it's one of these metrics to compare probability distributions. It's interesting to note that it's asymmetric. You wouldn't get the same value of doing p distance with q compared to q distance with p. And the way that you calculate this is by looping through each of the logits. So you have 10 logits in the case of MNIST. So we're comparing the probability density that p put on, say, 0 and q put on 0, then p put on handwritten digit label 1, q on 1, and so on until we get to 9. And we sum this up, and this is the Kullback-Leibler divergence for comparing the difference between two probability distributions, in this case, this teacher network and the student network. So in the hyperparameters we're exploring are alpha, the weighting of the sparse categorical loss with the ground truth one hot encoded labels, and then the KL divergence between the teacher and student probability distributions. And then we have temperature equals 10 to smoothen out the distribution produced by the teacher network. So now we call .fit, passing in our data, and then evaluate, passing in our data as well. And so then after 3 epochs, we achieve 97.5% accuracy, similar to the teacher model. It's really going to be, this data set of using MNIST is a bad proxy for the actual metrics. So I wouldn't really look at the performance. I'd really just try to understand this code for designing your own custom experiments. All of these models are going to fit MNIST basically perfectly. So the tutorial concludes by using the student scratch that we got from our initial cloning, where we use this syntax of student scratch equals keras.Models.clone model, passing in the student model to have the same initialization. And then we also see the performance of training it from scratch without any knowledge distillation. But again, these metrics, in my opinion, are kind of useless because all these models can fit MNIST perfectly. But to summarize, I think from this tutorial, you should have a really good sense of how to implement a custom class that has this custom kind of loss function and implements custom training steps and two loss functions, particularly with this weighting of the alpha. I think just if there's anything to take away, I think it's really these 4 lines of code or generally this class of distiller. So hopefully from this, you have all the tools you need to do any kind of experimentation with knowledge distillation. So thanks for watching, and please subscribe to Henry AI Labs for more deep learning and AI videos, and please check out the rest of the Keras Code Examples playlist.